Hello there, good people. How's it going? Welcome to my channel. My name is Marco, and today I'm at episode number 7 in this Python Projects for Beginners series. Today I have something special. It's not really a project, but more of an implementation of some particular algorithm. What am I talking about? I'm talking about binary search. Marco, why isn't it a project? Well, basically the algorithm is already there. I just need to implement it. And honestly, as far as I'm concerned, I love to try and implement all sorts of algorithms. They're good for your brain, they make you think, and there are so many that apply to many different scenarios. And in an interview or in normal life as well, they might give you the edge against the competition. After all, mental elasticity is one of those highly demanded skills, so it's always good to have it. Despite not being indispensable to become a software developer or a web developer, let's say that everybody recommends to learn the basics of algorithms and data structure because, after all, they really improve and increase your, let's say, awareness level when you're coding. You become mindful of time complexity, of memory management. It's definitely something worth, spending time as a beginner. On this subject, I strongly recommend the 006 course that is totally available online on YouTube by the MIT. Yes, that MIT. It's a compound of, I think, 24 videos and 1 hour each on average, and it is a complete overlook on algorithms and data structures. It is absolutely worth it. It's from 2011, but these things never actually change, so it's totally worth it. Totally up to date, anyway. I'm going to put the link down below if you wanted to give it a look. Now, back to the project. So, binary search. First of all, I need to make a few things clear, because there might be some confusion around this topic. Binary search is an algorithm to search an item in a collection, be an array, a list, a dictionary, you name it. It must not be confused with binary trees, which is a type of data structure. So the two things are completely different. Secondly, binary search is one of the many searching algorithms out there, and honestly, even one of the easiest to implement and understand, which is very important when learning algorithms because you want to understand it. How does that work? Well, it has a pretty clever solution to look for items in a collection, and it follows this so-called divide et impera logic, which is divide and conquer, where the collection gets divided in half each time until the item is either found or not found. In this regard, I need to specify one thing, which is fundamental for this algorithm to work, and that is the collection must be sorted. The logic goes like this. You go to the middle of a collection, you check if that is the number you're looking for. If it is, well, great. You return it, or you return the index, you return what you want. You're done with the algorithm. If it's not, well, okay, is it bigger or smaller? If the middle element is bigger, since the collection is sorted, I know that my number must be or could be on the left branch. Why do I say could be? Because the item might not be in the collection at all. This left branch now becomes my new array, and I'm just gonna repeat what I've done so far, but with this new branch. So I just check the middle, I divide, I check the middle. If it is the number I'm looking for, it's great. If it's not, I'm just gonna slice again, the same way I've done so far. Why is this so convenient? Couldn't I just check every item in the collection one by one? Well, absolutely. This is what is known as a brute force approach or a linear search. You just go through the entire collection. Even though that is a possibility, when talking in terms of algorithms, we need to keep in mind the time complexity of the implementation. What does tell me whether an algorithm is better than another one? Well, if it takes less time, it is better. Of course, you might also want to consider the context for the algorithm to work, because some algorithms don't work in certain scenarios. For example, this one, we need a sorted array. If we had an not sorted collection, we couldn't use binary search. In this particular case, binary search has a logarithmic complexity. And if you're new to programming, you probably never heard of this. Time complexity, logarithmic, linear, you don't know what it means. I got you covered. The complexity takes the number of items the algorithm needs to process into consideration. A linear complexity is very easy to understand. It's probably the easiest because the more the items, the longer it runs, and it does it in a linear fashion. So if I double the items, I double the time. Logarithmic grows a bit slower. It's not linear. This is why it's perfect for very large collections. Because if I double the items, I will not double the time, but the time will increase by the log of its items. I understand this is a lot of information to take in all at once, but I just need to specify one more thing that is pretty important for this project. There are many ways I could implement this, but I'm just gonna try two methods. I can use recursion, or I can use the iterative version, so using for loops or while loops. You might wonder what recursion is, and let's say that it is a pretty advanced topic, although it is very easy to explain and understand. However, it might become extremely difficult to implement sometimes. Recursion happens when a function calls itself inside said function. It has kind of a circular structure. As such, we need something that somewhere breaks the cycle. Otherwise, it might go on indefinitely. That breaking is called a base case. So when the function encounters that specific condition, it will stop calling itself. It will all be clear when you actually see the code. In this project, I will do it both ways, so using recursion and iteration. And I'll also show you why such an algorithm can become useful sometimes. After this super long introduction, it's time to take a look at the code. Okay, so I got both of the methods implemented, the recursive and the iterative one. And starting from the recursive one, I just take in the number I'm looking for and the collection it is supposed to be. And at the start, I'm checking if I actually have an array, so basically if the array exists. And this is due to the logic of recursion. So if I keep slicing and I finish all the operation, basically I will get to a point where I don't have an array anymore. And that will mean that the number is not present in the collection. So I need to handle this case. If I don't have an array, I just return none because the number is not in there. Now that I handled this case, I just go to the middle element and I pick the middle using the floor operation. This is basically, it returns an integer out of the length of the array, which sometimes is an odd number. But I want an integer so that I can use it as an index. Then I go to the middle element and I check if it's equal to the number I'm looking for. If it is, well, the job is done. So I just return the number. If it's not, there are two possible cases. One is that the middle element is bigger. And since, as I said, the array is sorted, I know that the number I'm looking for needs to be to the left of the middle. So what I do, I go to the left. Basically, I'm returning the same function, and this is where the recursion happens, with the number I'm looking for, but this time the collection will be sliced, and this slice represents the left branch of the original collection. The syntax is very simple. This basically means from the start to the middle index, and in this case the middle is not included, and I don't want to include it because if you check right here, I've already checked that the middle element is equal. So if I got here, it means that it's not, so I don't want to have it again in the process. Similarly, if the element in the middle is smaller than n, then it must be to the right of it. So I just return the function, but this time the slice will be of the right branch, and again I don't want to include the middle element because I've already checked it. Now there is one important thing I like to focus here, which is that I'm actually returning the binary search recursive function, and the reason for this is that when the process is done, I just want to basically stop the recursion. And what this does, when you're using recursion, the compiler creates what is called a stack of operations. So a stack can be thought as a group of boxes, one on top of each other. For example, if in my search for the number I have to call the function, or the function calls itself like 4 times, the first time would be on the bottom, then it calls itself the second time, third time, and the fourth time. And let's say that the fourth time I found it, and then it returns n. So the stack is clear from the top to the bottom, so that will return n. The operation below it is waiting basically for the return value of the function above. Since the function above returned n, now the function below knows that the return value is n, and so it will return n itself, and it will be cleared and it will return, and the stack would be, one step below, and so forth until the end. So it is very important for me to use the return statement here. Onto the iterative version, I basically take in the same arguments, the number I'm looking for and the collection where I'm looking. But this time I'm basically checking another exit condition, which is that the length of the array must be greater than 0, because if I keep slicing the array, I will get to a point where the length is 0. It basically means that I didn't find a number. And so when I exit this loop, I just return none, as before. When I get into the loop, the logic is basically the same. So I pick the middle element with the floor operation so that it is an integer. I check that the middle element is equal to n. If it's so, I return it. If it's not, so it's greater, I go to the left. This time I'm changing the original array so that when it goes up top to the while loop, the array now would be just the left branch. And so I continue. This sends me to the beginning of the loop. If it's smaller, well, then I just slice again, giving it the right branch, and I continue. And this is actually exactly the same, but it doesn't use recursion, it uses a while loop. Now, I wanted to show you some use cases for this algorithm. Please notice that all the most used programming language nowadays already have this kind of algorithms implemented. But again, just consider this an exercise, a very good exercise. Now, one use case for the binary search, it could be to verify if an element is actually in an array. And in this case, I'm verifying it with recursion, so with the recursive version of the algorithm, and with the iterative version of the array. The result is basically the same. But again, I call the function, and if it returns something, so basically remember that if you didn't find a number, it returned none, and none in Python is considered false. So this entire operation will be false, and if I find something, I return true. It means that it is in the collection. If it's not, it returns false. And it works the same for both the implementation. Okay, now I can try and run it with an input list that is not sorted, and it's very important that it is sorted. So I'll use the sort method in Python, and then I'll just print if is in an array, and 9 it is not, so it should give me false. Let's see if this happens. It actually does give me false. Let's say that I'm looking for 7, which is in the array. So the first one should give me true, and the second one should give me false. And that is the case. So as you can see, it works. Both of the implementation works. Let's try again. Through right here, I'm looking for 10, and yes, okay, it works perfectly. There is one last thing that I'd like to explain here, and it's kind of a recommendation for a better syntax. As you can see here, I'm basically using 3 lines to say if I have a result from this call, from the call of this function, well then I return true. If the return is none, well then I return false. Functions that return Boolean values are kind of tricky sometimes, but all this syntax, all these lines of code can be actually summarized in one simple line, which is basically I can return a statement. So if I return a statement, and that statement usually returns false and true values, so I can use that return value in this function. So I just need to do the return search recursion array is not none. What does this do? Well, basically this is a statement, and this statement is true only when the return value of this function is not none, which is what I want. It means that the number is in the array. When this function returns none, this will be false, and so I return false. In the other case, I return true. So basically it does the same. If I try it again and run it, it should just return the same. It's just a little bit more elegant, and yeah, it's a nicer thing to see, and probably is even, I don't know, more legible. Well, this was fun, and I really hope you could learn something from this and actually get inspired to exercise your algorithms knowledge. It is something that I strongly recommend because it is fun, it is challenging, and overall it will improve the way you think and write your code. There are also many other ways you could implement this specific algorithm. For example, instead of the number, you could return the index where that number is. You need to tweak it a little bit, but it can be done. Okay, really. Thank you very much for watching. I really hope to see you in the next video. And I think it's all for now. If you like this video, please leave a like so that more people can see it. And don't forget to subscribe, because why not? Leave comments down below if you had any comments or any suggestion for new projects and stuff, or if you had any question. I'll see you later. Stay tuned for more. Bye bye.